Okay, in last class we have seen the ratio of specific heats Cp by Cv equal to gamma. So in order to prove this Cp by Cv by gamma by using Maxwell's equations, first of all we have written the equation of Cv, and after that we have written the equation of Cp. What is Cv? Dou Q by dou T at V. The amount of heat energy required to rise the temperature of 1 gram mole of gas through 1 degree centigrade when the volume is constant. It is called as specific heat at constant volume. Similarly, specific heat at a constant pressure Cp. So, as per the definition, Cp will be written as dou Q by dou T at P. Now, we have to prove that Cp by Cv equal to constant, that is gamma. So, we learned how to prove Cp by Cv equal to gamma. First of all, for that, I have taken the volume elasticity. So, the volume elasticity, as per the definition, it can be written as stress by volume strain. From that, E equal to minus V into dP by dV. So, this volume strain, just volume elasticity can be written in the adiabatic process and as well as in the isothermal process. So, after that, if you take Es by Et, so you do on solve these equations. Finally, you can prove that Cp by Cv, Es by Et equal to Cp by Cv equal to gamma. In a similar manner, we have also proved that the difference of specific heats equal to R, that means universal gas constant. Cp minus Cv equal to R. You know Cp and you know Cv. So the relation between these two, we can, if you take entropy as a function of V comma T, then the relation between these two can be written as Cp minus Cv equal to T into dou P by dou T at V into dou V by dou T at P. So, from this, we have proved that Cp minus Cv equal to R. So, for that, we have taken a perfect gas, a gram mole of perfect gas. So, what is the equation for a perfect gas? PV equal to nRT, where n equal to 1. We have taken 1 gram mole of gas. That is why n is kept as 1. So, then PV equal to RT. If you differentiate this equation with the temperature at a constant V, you can get this value, dou P by dou T at V equal to R by V. Similarly, if you differentiate this equation with respect to T at a constant P, then you can get the value dou V by dou T at P equal to R by V. So, if you substitute these two equations, these two values in the above equation, you can get Cp minus Cv equal to R. These are the applications related to Maxwell's equations. So, we have seen 3 applications. What are those? Clausius-Clapeyron equation, and after that Cp by Cv equal to gamma, and after that Cp minus Cv equal to R. Now, in today's class, we can see Joul Thomson effect or Joule Kelvin effect. What is Joule Thomson effect or Joule Kelvin effect? You see, it is a very important one. At the same time, you must read it. Okay. So, what is Joule Kelvin effect? If you allow gas to pass through a porous plug from the region of high pressure to the region of low pressure, then there will be a change in its temperature. This was first observed by Joule and Kelvin, and hence it is called as Joule Kelvin effect or Joule Thomson effect. So once again, I repeat this. So if you allow a gas to pass through a porous plug, a material like cotton, from the region of high pressure to the region of low pressure, then there will be a change in its temperature. This was first observed by Joule Kelvin. That is why this effect is called as Joule Kelvin or Joule Thomson effect. So Lord Kelvin is the జౌల్ థామ్సన్ కి లార్డ్ కెల్విన్ అనే బిరుదు ఇవ్వడం వలన దీన్ని అతన్ని కెల్విన్ అని కూడా మనం పిలుస్తుండడం జరుగుతుంది. కనుక దీన్ని జౌల్ కెల్విన్ ఎఫెక్ట్ అని కూడా అంటారు, ఆర్ జౌల్ థామ్సన్ ఎఫెక్ట్, వాట్ ఎవర్ ఇట్ మే బి. ఓకే, సో దిస్ ప్రాసెస్ ఆఫ్ passing of gas under such conditions is called throttling process. So this process, passing of gas from from region of high pressure to from the region of low pressure, is called throttling process. You see, this is the figure related to this process, throttling process. You see, this is the high pressure region and this is the low pressure region. This is porous plug, a cotton type of material. So if you allow the gas pass through this porous plug type of material from high pressure region to low pressure region, then there will be a change in its temperature. So this effect is called Joule Thomson effect or Joule Kelvin effect, or this process is also called as throttling process. Okay, so all the gases in this process, all the gases suffer a change in its temperature. At ordinary temperature, all the gases except hydrogen and helium suffer a fall in its temperature. So during this throttling process, the temperature of all gases decreases, whereas at ordinary temperature, the temperature of helium neon gases will increase. Instead of decrease, the temperature of helium neon gas increases, slightly rises. So we can I can give a clarification on that later. Okay, now the change in temperature is directly proportional to the pressure difference on the two sides of the plug. So I already said that all the gases except helium and neon can have the temperature of all the gases can reduce due to this throttling process except helium and neon gas. Their temperature slightly rises at ordinary temperatures. So the change in temperature is directly proportional to the pressure difference between the high pressure region to low pressure region in throttling process. So now we are going to find out the coefficient of throttling process. Coefficient of throttling process. So how we are going to find out, we can see. Okay. So in the throttling process, the total enthalpy of the gas remains constant. This is main important point. In the throttling process, the total enthalpy of the gas remains constant. That is why we can start to derive mu, the coefficient of throttling process, from this equation. What is that? H equal to U plus PV equal to constant. H equal to constant. What is H? U plus V. What is U here? Internal energy, and PV is the work done. Therefore, H equal to U plus PV equal to constant. Why? Because in throttling process, total enthalpy remain constant. If you differentiate this equation, So you can get du plus pdv plus vdp equal to 0. Why? Because if you differentiate the value constant, you can get 0 value. So you know what is du? TDS minus PD. So if you substitute this value in place of du plus, we can write the values as it is like this. So instead of du, you have to write TDS minus PDV, and the remaining terms you have to write as it is plus PDV plus VDV. Whereas you see this minus PDV and plus VDV will be cancelled out. Then you can get TDS plus VDV equal to 0. Now, let us suppose, let us take S is a function of P comma T. సో మనం ఎంట్రోపీని ప్రెషరు మరియు ఉష్ణోగ్రతల యొక్క ఫంక్షన్గా తీసుకున్నట్లయితే ఇట్ కెన్ బి రిటన్ యాజ్ ఎస్ ఈక్వల్ టు ఎఫ్ ఆఫ్ పిటి. సో ఎస్ కెన్ బి టేకెన్ యాజ్ ఎ ఫంక్షన్ ఆఫ్ పి కామా టి ఆర్ ఇట్స్ ఎ ఫంక్షన్ ఆఫ్ v comma t like that. So according to the situation, we can take entropy as a function of different variables. So here in this situation, we can take S as a function of P comma T. Why? Because this is the topic related to pressure and temperature only. Why? Because we are allowing the gas passing through the porous plug from the region of high pressure to the region of low pressure. So this is the process, entire process related to pressure and temperature. That is why I am taking S as a function of P comma T. Now, if you differentiate this equation, ds equal to, as you know how to differentiate this equation, so dou s by dou p at t into dou. So we can take one variable as a constant. After that, we can take the another one as a constant. If you take t as a constant, this can be written as dou s by dou p at t into dp plus dou s by dou t at p into dt. Okay, now you have to substitute this value in the above equation. What is the above equation? TDS plus VDP equal to 0. If you substitute this ds value in this equation in place of ds, so you have to write like this: T into dou s by dou p at t into dp plus dou s by dou t at p into dt. Plus, you can write the other value as it is. What is the other value? Vd. Okay, plus vdp equal to 0. Now, I should multiply with t with t with t. So t into dou s by dou p at t into dp plus t into dou s by dou t at p into dt plus vdp equal to 0. Now, if I take this temperature into the bracket, what will happen? T dou s. What is the value of T dou s? You already know about this value. T dou s equal to dou q. So now I can write dou q instead of T dou s. So T into dou s by dou p at t into dp plus dou q by dou t at p into dt plus vdp equal to 0. Now you know what is the value of this, what it gives, what this value gives us. Dou p by dou q by dou t at p gives us cp. So instead of this value, I can write cp. So t into dou s by dou p at t into dp plus cp dt plus vdp equal to 0. Now I can take these two values into the right hand side. So if I take these two values to the right hand side, this equation becomes, you see, cp dt equal to, this value becomes minus value, minus t dou s by dou p at t into dp. This value becomes minus 1 minus VdP. So, from Maxwell's fourth equation, dou S by dou P at T equal to minus dou V by dou T at P. Now, instead of this value, I can substitute this value with the Maxwell's fourth equation. So, instead of dou S by dou P at T, I can write minus dou V by dou T at P. So, substituting this in the above equation, this equation becomes, you see, Cp dt equal to T into, instead of this value, I can write dou V by dou T at P. Here we have minus value, and again we have here minus value. Minus into minus plus. So T into dou V by dou T at P into dP minus Vd. Now Cp dt equal to, now I can take dP as a common, then this equation becomes dP into T dou V by dou T at P minus V. Okay. So now if you take this dP value to the left hand side, Cp left hand side, and take the Cp to the right hand side, then what will happen? dt by dP equal to 1 by Cp into T of dou V by dou T at P minus V. You see, dt by dP equal to 1 by Cp into T of dou V by dou T at P minus V. But I already said that in this throttling process, the enthalpy remain constant. That is why I can write this equation as dou T by dou P at H. So if I take any value as a constant, this differentiation becomes partial differentiation. So dt by dP can be written as dou T by dou P at H equal to 1 by Cp T into dou V by dou T at P minus V. This is the expression for cooling produced by Joule Kelvin effect. In the above equation, dou T by dou P at H is called Joule Kelvin coefficient of expansion. So this value is called Joule Kelvin coefficient of expansion, and this is denoted by mu. And this is denoted by mu. Therefore, we can write this equation as, how I can write this equation? Instead of dou T by dou V at H, I can substitute mu value. Mu equal to 1 by Cp T into dou V by dou T at P minus V. This is the equation for Joule Kelvin coefficient of expansion. Now, if I substitute all the values, if mu is positive, then there is a cooling effect due to this throttling process. So if mu becomes negative, then there is a heating effect due to this throttling process. If mu is 0, the gas neither get cooling or heating. So this is neither cooling. So like this, we can get the like this we can explain the Joule Kelvin effect or throttling process. So this is what is about Joule Thomson effect, and this is called Joule Kelvin coefficient of expansion. Okay, so this is what is about Joule Thomson expansion or Joule Kelvin effect or throttling process. So we can see once again. So what is Joule Kelvin effect? Whenever we allow to pass the gas through the porous plug from the region of high pressure to the region of low pressure, then there will be a change in the gas. Then there will be a change in the temperature of the gas. This effect is called as Joule Kelvin or Joule Thomson effect. Okay, so at ordinary temperatures, at a room temperature, all the temperature of all the gases will decrease, whereas the temperature of helium neon gas slightly rises. Okay, so this process is also called as throttling process. Okay, in the throttling process, the enthalpy of the gas remain constant. So H is constant. As you know, what is the value of H? U plus PV equal to constant. So first, if you differentiate this equation, you can get this value: du plus pdv plus vdp equal to 0. If you substitute the value of du, you can get this value. After that, if you take entropy as a function of P comma T, and then take the value of differentiation value of ds, then substitute this value in the above equation. After that, by using the Maxwell's fourth equation, this value is to be replaced. Then after that, finally you can get that dt by dp equal to 1 by cp t of dou v by dou t at p minus v. So as this throttling process, as in this throttling process, the total enthalpy is constant. We can write this equation as dou t by dou v at h equal to 1 by cp t into dou v by dou t at p minus v. This value can be replaced by the notation mu. What is that? Mu represents Joule Kelvin coefficient of expansion. Therefore, mu equal to 1 by Cp T of dou v by dou t at P minus V. So here, if you get the mu value as positive, then there is a cooling effect due to this Joule Kelvin effect. If you get mu as a negative, then there is a heating effect. So if mu becomes 0, that represents that either the gas neither the gas will cool, or either it will be heated up. Okay, so that is what the mu value represents. Okay, now if a perfect gas applied for this Joule Kelvin effect, what will happen? So Joule Kelvin effect for a perfect gas. So, if you allow the perfect gas passing through the porous plug from region of high pressure to the region of low pressure, what will happen? So, you see, what is the equation for perfect gas? PV equal to N naught. Suppose if you take 1 gram mole of gas, then N becomes 0. Sorry, N becomes 1. Then PV equal to RT. From this, V equal to RT by V. RT by P. So, if you differentiate this equation with respect to T at a constant pressure, what will happen? Here V equal to RT by P. So, dou V by dou T at P equal to 1 by P into R, where if you differentiate the temperature with the temperature, we can get the value of 1, where R is a universal gas constant. That is why dou V by dou T at P will become 1 by P into R. So, if you substitute this value in the Joule Kelvin coefficient of expansion, see, dou V by dou T at P, dou V by dou T at P. So, what will happen? So, what is the value of dou V by dou T at P? 1 by P into R. So, therefore, mu equal to 1 by Cp of T into R by P minus V. Here, what will happen? Mu equal to 1 by Cp of RT by P minus V. But if you substitute PV in place of RT, as you know, PV equal to RT, T and P will be cancelled out. Mu equal to 1 by Cp V minus V. That is mu equal to 0. That means there is neither cooling nor heating in case of perfect gas. In case of perfect gas. So this is what will happen when a perfect gas is allowed to pass through a porous plug from the region of high pressure to region of low pressure. That means Joule Kelvin effect for a perfect gas. So, because of the throttling process, the temperature of the perfect gas will not change. That means perfect gas neither undergo for cooling or heating. Okay. So, now if you go for van der Waals gas, what will happen? Joule Kelvin effect for van der Waals gas. You know what is the equation of van der Waals gas? P plus A by B square into V minus V equal to RT. So you should remember this equation. This is the equation gives us van der Waals equation. P plus A by B square of V minus V equal to RT. Differentiating this equation with respect to T, taking T as a constant. Why? Because you have that value in the new equation, Joule Kelvin coefficient of expansion value. So that is why I am taking the differentiating value of this. I am differentiating this equation with respect to T, taking P as a constant. Now, let us see how to differentiate this equation. Here, I can take this value as a constant first, P plus A by B square into, I can differentiate this one, dou V by dou T at P, where A and B are constant. That is why this value becomes 0. Again, I can keep this value as a constant, I can differentiate this value. So, B minus B of minus 2A by V cube into dou V by dou T at P equal to R. Okay, now I can take this value as a common. Dou V by dou T at P, then this equation becomes R by P plus A by V square minus 2A by V cube into V minus V. Okay, now R by, now we can see step by step solvation of this equation. R by, okay, so you see, you know, P plus A by V square. What is the van der Waals equation? P plus A by V square of V minus V equal to RT. If you take this value to the right hand side, P plus A by V square becomes RT by V minus V. So, in respect of this value, I can write RT by V minus V. So, here see. So, in place of P plus A by V square, I can write RT by V minus V minus 2A by V cube into V minus V. So, now if I multiply with V minus V, both the numerator and denominator, what will happen, you see? So, R into V minus V whole by RT minus 2A by V cube into V minus V whole square. After that, R into V minus V whole by RT minus VA by V, 2A by V cube. So, what is the value of V minus V whole square? V square plus V square minus 2VV. So, again, R into V minus V whole by RT minus, if I multiply the values inside the bracket with the 2A by V cube, then what are the values I can get? So, 2A V square by V cube minus 2A V square by V cube plus 4A VB by V cube. So, by neglecting the higher values, I can get dou V by dou T at P equal to R into V minus V whole by RT minus 2A by V. Substituting this value in the equation number 3. As you know, mu equal to 1 by Cp of T into dou V by dou T at P minus V. So, instead of dou V by dou T at P, if I substitute this value, what will happen? 1 by Cp equal to RT V minus V whole by RT minus 2A by V minus V. Here RT and RT. If I take RT common here, I can get RT of 1 minus 2A by V RT. So, RT in the denominator, RT in the numerator will be cancelled out. I can get 1 by Cp of V minus V by 1 minus 2A by VRT minus V. If I take this value to the numerator, so this can be written as 1 by Cp of V minus T, 1 minus 2A by VRT to the power of minus 1 minus V. So, this can be written as 1 by Cp of V minus T. As per binomial theorem, it can be written as 1 plus 2A by VRT minus V. So, 1 by Cp of V minus D plus, if I multiply with these two values with the V minus B, then V minus B plus 2A into V minus B by V or T minus V. So, again, these minus and minus V values will be cancelled out, and I can, if I multiply V and B with the value of 2A by V or T, this can be written as 2AB by V or T minus 2AB by V or T minus B. Here V and V are cancelled out, and I can write it like this: mu equal to 1 by CV of 2A by RT minus B. So we can neglect this value, neglecting 2A by VR. So finally I can get this value. So for, if I apply Joule Kelvin process to the van der Waals gas, then the equation of Joule Kelvin coefficient of expansion mu becomes 1 by Cp of 2A by RT minus B. If 2A by RT equal to B, so what will happen if this value equal to B, then mu equal to 1 by Cp of B minus B, that equal to mu equal to 0. That is, the gas neither cooling nor heating. The corresponding temperature is called as inversion temperature and expressed by Ti. So, if this value becomes B, then what will happen? Mu will become 0. Now, the corresponding temperature to this value of B is called inversion temperature. So, this can be written from this equation. If 2A by RT equal to B, then 2A by RB equal to Ti. This is called inversion temperature. Suppose if I substitute that value, so mu equal to, you see, if I take B as a B from this bracket, that means if I take B as a common, then mu will become mu equal to B by Cp of 2A by B or T minus 1. B by Cp of, so instead of this value, what is that value? 2A by RB. I can write Ti value, then mu equal to B by Cp of Ti by T of minus 1. This is the inversion temperature, and this is a temperature at which we are running the process. So this is specific heat at constant pressure, and this is a constant. So mu equal to B by Cp of Ti minus T minus 1. You see, if T less than Ti, if T less than Ti, so what will happen? Mu is positive. If T less than Ti, so if a value which is in the denominator is less, then the fraction value is high. That means mu is positive. So that is why if T is less than Ti, mu is positive. That is, the gas suffers cooling. If T greater than Ti, so the temperature at which the process is running is greater than the inversion temperature of the gas, then mu becomes negative. That is, gas suffers heating. If T equal to Ti, then mu is 0. That means the gas neither cooling nor heating. Neither cooling nor heating. So this is how, if a van der Waals gas is applied in the, if a water well gas passes through the porous plug from the region of high pressure to the region of low pressure, that is, if Joule Kelvin effect applied for van der Waals gas, then this is the equation you can get, and these are the situation you can see. So if T is less than Ti, mu is the positive. That means the gas suffers cooling. If T greater than Ti, that means T, what is T here? The temperature at which the process is running is greater than the inversion temperature of the gas. then mu will become negative. That means gas suffers heating. So that is why the helium and neon gases suffers that is why the temperature of the helium and neon gases rises a little bit high. So after that, if T equal to Ti, that means mu is 0. The gas neither cooling nor heating. So this is how one can explain about Joule Kelvin effect or Joule Thomson effect or throttling process. So we have derived the equation for Joule Kelvin coefficient of expansion. After that, we applied this throttling process to perfect gas, and we applied this throttling process to the Van der Waals gas. If I applied throttling process to the perfect gas, mu becomes 0. That means the gas neither cooling nor heating. If I applied Van der Waals gas, you can get three types of gas cases. What are those? If T greater than Ti, mu becomes positive. That means the cooling effect may takes place. That means the temperature of the gas decreases. If T greater than Ti, mu becomes negative. That means the temperature of the gas rises. If T equal to Ti, then mu equal to 0. That means the gas neither cooling nor heating. Okay, so this is how one can explain the Joule Kelvin effect or Joule Thomson effect. So once again, I can give the definition. What is Joule Kelvin effect? If a gas allowed to pass through a substance like from porous plug from the region of high pressure to region of low pressure, then there is a change in the temperature of the gas. In most of the cases, at ordinary temperatures, the temperature of the gas, all the gases temperature will get reduced, but except helium neon gas temperatures will rise slightly a bit. Okay, so from that onwards, I can derive the equation of coefficient of Joule Thomson expansion mu. So after that, I applied this throttling process to perfect gas, and I applied this process to Van der Waals gas. Okay.